Hello, you are most welcome. I'm teacher Ivan from Wuna Educational Services. I welcome you to our first lesson of heat transfer. We are looking at A-level physics and we are in heat. So we shall start with discussing heat transfer. And among the heat transfer processes, we shall start with the conduction. So we are calling it thermoconduction. Perhaps before we come to the main part for today, there are questions, they are research questions whose answers are to be found by you. The first question asks us to define conduction. The second tells us to describe the mechanism of heat conduction in metals and nanometals. And the third asks for explanation why metals are better conductors than nanometals. Those are three research questions whose solutions are to be researched and answered by you. Perhaps there are key areas that must not miss out. For instance, in the definition of conduction, you must talk about the temperature difference because heat is transferred due to temperature difference. You must also show that in conduction, heat is transferred but without the movement of the material molecules. That is very important. In the second question, they want us to describe the mechanism of heat conduction in metals and nanometals. So as you research, you'll find out that in metals, heat is transferred by two mechanisms. That is the atomic vibration and the mobile electrons. Whereas in nanometals, it is by only atomic vibration. That's why in heat, we have nothing like an insulator, because as long as it has atoms, then heat is transferred by atomic vibration. And actually that also answers the third question as to why metals are better conductors than nanometals. Because we've seen that in metals, heat is transferred by two mechanisms. That is the atomic vibration and the mobile electrons. Whereas in nanometals, it's by only the atomic vibration. So that clearly shows why metals are better conductors than nanometals. So please research more and add on that. Otherwise, today's major interest is in thermoconductivity. Yes, after researching and knowing the mechanisms of heat transfer in metals or in nanometals, we've seen that if they are metals, then heat is transferred by two mechanisms, atomic vibration and the free-moving electrons. But my question is, why is still there a difference between the rates of heat transfer in metals? The answer is thermoconductivity. For instance, if we are to compare copper and aluminium, copper is better conductor than aluminium. What makes copper a better conductor than aluminium? Yet they are all metals having the free moving electrons and having the atoms that could vibrate. Our answer to that is thermoconductivity. Therefore, thermoconductivity is the rate of heat flow through a material per unit area per unit temperature gradient. So, in brief, to understand this better, let us consider a conductor of thickness L, cross-sectional area A, having temperatures theta 1 and theta 2 at its ends. So this is our conductor of thickness L, having temperature theta 2 and 1 at the ends. Assuming theta 2 is greater than theta 1, then it means that this end is hotter than the other end. And that's what causes heat transfer. So the rate of heat flow per second is directly proportional to the cross-sectional area A of the conductor, and also directly proportional to the temperature difference across the ends of the conductor. But it's inversely proportional to the thickness of the conductor. And therefore, that brings us to factors that affect the rate of heat transfer through a conductor. There are three factors. We've seen the cross-sectional area, which is directly proportional, meaning increase in cross-sectional area increases the rate of heat flow. We've seen the temperature difference, which is also directly proportional, meaning that as you increase the temperature difference between the ends of the conductor, the rate also increases. But as you increase the thickness of the conductor, the rate reduces. That's why the thickness is inversely proportional. So we are going to change this statement into a mathematical statement, and we see how we bring in thermoconductivity, or the origin of thermoconductivity, which is today's major interest. Mathematically, this is how we shall write the above statement. The rate of heat flow is directly proportional to the cross-sectional area A, the temperature difference, but inversely proportional to the thickness L. So if we are to replace the proportional sign with a constant K, then we shall have the rate of heat flow as Ka, where K is the constant, A is the cross-sectional area, then the temperature difference over the thickness. But when we combine these two, the temperature difference over the thickness, it's what gives us what we call the temperature gradient. And therefore, we can define temperature gradient as the temperature difference per length, or the ratio of temperature difference across the ends of a conductor to its thickness or length. So we have brought in the constant K, and K is what we call the coefficient of thermoconductivity. So this is the origin of coefficient of thermoconductivity, which depends on the nature of the material for a given conductor. That's why we can have two metals but having different rates of heat flow because of thermoconductivity. So the units for thermoconductivity, we shall derive them from the formula. Since we've seen that the rate of heat flow is given by Ka, theta 2 minus theta 1 over L, where K is the thermoconductivity, then for us to be able to derive its units, we must make it the subject, whereby we shall have K, the thermoconductivity, as the rate of heat flow over the cross-sectional area over the temperature gradient. So we shall take this up. When we simplify this mathematically, we get L over T, which is the rate of heat flow, over A into theta 2 minus theta 1. And then from there we can get the units. L being thickness, it's in meters. This being the rate of heat flow, we can write it as joules per second, or we can combine to get a watt. Then area is in meters squared. Then this is temperature difference, which is in Kelvin. So we can reduce meter and meter squared to give us per meter. So it gives us joules. This one is reduced per meter per Kelvin. So that is how we get the units for thermoconductivity K. We can combine these to give us a watt. So it is watt per meter per Kelvin. That is how we get the units of thermoconductivity. Then from there we shall come back and look at the factors which affect the rate of heat flow through a given material. From the equation for rate of heat flow, we've seen that the equation is given by rate of heat flow equaling to thermoconductivity K times the cross-sectional area times the temperature gradient. And therefore, there are three factors. We have thermoconductivity, which depends on the nature of the material. So we shall call this nature of the material. We have the cross-sectional area, and we have the temperature gradient. We combine the difference over the length to give us temperature gradient. So those are the three factors that affect the rate of heat flow through a material: the nature of the material of the conductor, the cross-sectional area, and the temperature gradient. Those are the three factors. So we've seen the temperature gradient of a conductor as the ratio of the difference in temperature between the ends of the conductor to the length of the conductor. That's the definition for temperature gradient. We have examples concerning the above equation. Example 1 gives us aluminum plate of cross-sectional area 300 centimeters squared, thickness of 5 centimeters, and has one side maintained at 100 by steam, and the other side is maintained at 30 degrees Celsius. So the energy passed through the plate at the rate of 9 kilowatts. So this is the power or the rate at which heat is being passed through the aluminum plate. They want us to get the coefficient of thermoconductivity of aluminum. So from our equation, or the general equation for the rate of heat flow, which says that the rate of heat flow, that is Q over T, equals to thermoconductivity K times the cross-sectional area times the temperature gradient, which is theta 2 minus theta 1 over the thickness. So they want us to get the thermoconductivity K. We shall make K the subject, that is K equaling to, when we multiply through by L, it gives us L Q over T over A into theta 2 minus theta 1. And now we shall run back to our question and summarize the given information. So from the question, we are given the cross-sectional area A as 300 centimeters squared. We are given the thickness L as 5 centimeters. we are given the temperatures. Theta 2 is 100 and the theta 1 is 30 degrees Celsius. And then we have the energy, or the rate at which energy is being passed through. That is Q over T, which is 9 kilowatts. 9 kilowatts, the same as 9,000 watts, because kilo is 1,000. So we can substitute. Our L is, but as we substitute, everything has to be in its SI units. So we must not forget to change the 300 centimeter squared to meter squared, 5 centimeter to meter. These ones we cannot change, or we might not change because we are going to subtract. After all, it is a difference. Whether we change to Kelvin or not, the difference remains the same. Then we substitute for Q over T to get the thermal conductivity K. So that has been our first lesson on heat transfer, and we are particularly looking at thermal conduction. So please, if at all you enjoyed the lesson, I request you to comment, share, and like. But most importantly, if you are new, hit the button and subscribe, hit the bell to get notified whenever we have such videos. Otherwise, I'm teacher Ivan from Wuna Educational Services. I wish you the best. I hope to see you in the next lesson. Bye-bye.